The electric dipole is defined as the system of two equal and like charges at a finite distance from each other. Let us consider two charges q and minus q separated by the distance a. The dipole moment is defined as the product of one of the two charges and the distance between them. It is a vector quantity having direction from the negative charge to the positive charge. It is denoted by vector p. To determine the field of electric dipole, we arrange the Cartesian coordinate system in such a way that its z-axis coincides with the dipole and the midpoint of the dipole coincides with the origin. In such a situation, the position vector of charge plus q is vector r1, 0, 0, a upon 2, and the position vector of charge minus q is vector r2, is 0, 0, minus a upon 2. According to the definition, the intensity of electric field, or in short, the electric field at point vector r is vector E vector r is equal to k into q vector r minus vector r1 upon modulus of vector r minus vector r1 cube minus q into vector r minus vector r2 upon modulus of vector r minus vector r2 cube. Now, vector r minus vector r1 is equal to x, y, z minus 0, 0, a upon 2. That is equal to x, y, z minus a upon 2. And vector r minus vector r2 is equal to x, y, z plus a upon 2. Moreover, modulus of vector r minus vector r1 cube is equal to x square plus y square plus z minus a upon 2 raised to 2 raised to 3 upon 2. And modulus of vector r minus vector r2 cube is equal to x square plus y square plus z plus a upon 2 raised to 2 raised to 3 upon 2. If r is greater than r1 and r is greater than r2, that is equal to modulus of vector r minus vector r1 cube is equal to x square plus y square plus z squared minus za plus a square upon 4 raised to 3 upon 2. Neglecting a square upon 4 in comparison with r square, that is equal to r square minus za raised to 3 upon 2. Therefore, 1 upon modulus of vector r minus vector r1 cube is equal to 1 upon r square minus za raised to 3 by 2 equal to 1 upon r cube into 1 minus za upon r square raised to minus 3 upon 2. Using binomial theorem and neglecting the terms of higher powers, we get 1 upon modulus of vector r minus r1 cube is equal to 1 upon r cube into 1 plus 3za upon 2r square. Similarly, 1 upon modulus of vector r minus r2 cube is equal to 1 upon r cube into 1 minus 3za upon 2r square. Substituting all these values in equation vector E vector R is equal to K into Q upon R cube into x, y, z minus a upon 2 into 1 plus 3za upon 2r square minus q upon r cube into x, y, z plus a upon 2 into 1 minus 3za upon 2r square. Expressing this field in terms of its x, y and z components, we get vector Ex vector R is equal to kq upon r cube into x1 plus 3za upon 2r square minus 1 minus 3za upon 2r square. That is equal to kqa into 3xz upon r raised to 5 that equals to kp into 3xz upon r raised to 5. Therefore, Ex vector R is equal to kp into 3xz upon r raised to 5. Similarly, we can write Ey and Ez components. Ey vector R is equal to kp 3yz upon r raised to 5. Ez vector R is equal to kp 3z square minus r square upon r raised to 5. Using equations, we can obtain the field vector near point xyz if the separation between two charges of the dipole is very small. It is called point dipole. And in such cases we can find the electric field of a dipole at any given point with the help of equations